So to calculate the moment of inertia of mass distribution, we would need to use infinitesimal small pieces of mass, we will label as dm, and write down the moment of inertia by evaluating an integral over the infinitesimal masses rather than doing a discrete sum over finite masses, which we have applied in the previous examples. So for a mass distribution, moment of inertia is going to be an integral of r squared times dm. Let's look at some examples. Here we need to calculate the moment of inertia of a thin rod of mass m, of a total mass m, and the total length of L rotating through its center, which is shown in the diagram. Now to do this problem, we are going to see that this thin mass is a 1D object. We're going to consider it to be a 1D object that is sitting along the x-axis. Its center of this rod is going to be at the origin. Now we're going to divide the mass into small element of masses, and we're going to label them as dm. And the length of this small mass is going to be dx. And x is the location of this small mass increment. All of this is shown here. So this is the small mass dm. It has a length of dx. It is located a position of x from the rotational axis. To go any further, we want to define linear mass density. We're assuming the mass of this rod is linear, it's uniformly distributed. And lambda is usually used for linear mass density, and lambda is equal to the total mass over L, or total mass is equal to lambda times L. Okay, so what about the mass of an infinitesimal element? Then that is going to be dm is equal to lambda times dx. Now we can use the equation for moment of inertia for mass distribution. So we have integral of r squared times dm. I'm going to substitute that dm is equal to lambda times dx, which I've done here. The limits of integration, we are integrating from negative L over 2 to L over 2, which you see here. Lambda is a constant. We can bring it out of the integral. Then we can integrate this from negative L over 2 to L over 2, or another trick that I have learned in my calculus class was we'll go from, because of the symmetry, we go from 0 to L over 2, and we have it just will be multiplied by 2 times x squared times dx. And then x squared, integral of x squared is just x cubed over 3. You have the limits of integration, plug that in, and the moment of inertia ends up being lambda L cubed over 12. We usually want to represent moment of inertia in terms of m and L. So in order to get rid of lambda, we'll use this substitution that lambda is equal to total mass over L. And we get that moment of inertia is ml squared over 12. Now let's see how the moment of inertia would differ if the rotational axis is towards the end. Now we're going to just follow the same steps that we did in the previous problem. We have dm, which is the small mass increment, has a size of dx. It is located at a distance of x from the rotational axis. We will define linear mass density as total mass over total L, and the small mass is lambda times dx. We'll use the integral of r squared dm, but substituting in r here represents the position. For a 1D object, our position, if it's along the x-axis, this is going to be just x. R is going to be x. So we have x squared times dm. Substituting that in, you have lambda x squared, but the limits of integration, as you can see, it's going to go from 0 to L instead of negative L over 2 to positive L over 2. And that is mainly just the difference between this problem and the previous one. Bring out the lambda, do the integral, the moment of inertia comes out to ml squared over 3. There is a easier way to calculate the moment of inertia if we know the moment of inertia of an object through its center of mass, and the rotating object is not rotating at the center of mass. So we call this the parallel axis theorem. So in the parallel axis theorem, we say let m be the mass of the object and d be the distance from the axis, from the rotational axis through the object's center of mass to a new axis. Then we can use this parallel axis theorem, which is saying moment of inertia using the parallel axis is equal to moment of inertia through the center of mass plus md squared. Now let's apply this to the example that we have seen in the previous two slides, where you had we knew in the first part was to calculate the moment of inertia through the center of mass. Center of mass of a thin rod is going to be at the center, and we noted that that was 1/12 of the total mass times L square. Now, if the new rotational axis was at the end, we want to calculate the moment of inertia. We can use the integral, but we can use an easier way. If you don't like calculus, then this would be the easier way, which is saying the moment of inertia using the parallel axis theorem, but at the end is moment of inertia through the center of mass plus the mass of the object times the distance from the rotational axis to where the center of mass is. So this is what D represents. As you see here, D is equal to L over 2. That's what I have substituted in, that the moment of inertia through the center of mass is 1/12 mL square, and the D is L over 2. You square that, simplify, and then you get that the moment of inertia is equal to 1/3 mL square, which is the same thing that we have got in the previous slide. Let's look at how you would apply it to a 2D object. So now we have to calculate the moment of inertia of a uniform disk that is rotating through its center. This is the diagram of what that disk looks like. We are going to break this disk into small rings of mass dm. Each dm is located at a distance of r, and it has a thickness of dr, as you see here. Get it r. The limits of integration for r is going to go from 0 to r. So for surface mass density, we use sigma, that is equal to total mass over the total area, and then the total mass is just going to be sigma times area. If you look at the small teeny tiny mass increment, if we have uniform mass density, then that is sigma times dA. Well, for this object, this is a 2D object, the area is just going to be the surface area, or dA is just going to be the area, so this is just 2 pi r times dr. So then moment of inertia is just using the definition, plugging in the numbers, taking out the constants, using the limits of integration, integrating it, simplifying it, we will get the moment of inertia as mr squared over 2, which should be the same thing that you should see on the table listed in the previous slides. All right, let's talk about torque. Now, if you have a door and it is currently closed, if you want to open the door, you need to apply a force. If you apply a force very close to the rotational axis, the door is going to be very difficult to rotate. But if you do get it to rotate, it is going to move in this direction. If you were to apply a force from the opposite direction, F5, then the door is going to rotate in this direction. It's going to be very difficult to get it to rotate. If you apply a force towards the end of the door, it's going to be easier for you to get it to rotate in this direction. Much easier. You need to apply a smaller force to get it to rotate. If you apply a force in this direction, what would happen? Yes, the object should not rotate. If you apply a push from the angle at an angle other than the angle of 90 degrees, which are shown for F1, F5, and F4, you'll still get a rotation, but it is going to be less in strength. So based on our thought experiment, we can conclude the following, which is that only forces with a perpendicular component will produce a torque. And the radial distance dictates how effective a force is at producing a torque. Now, torque is angular force. It's a force that will cause an object to rotate. So just like how we talked about linear motion, a push will get a object to start moving linearly. So an angular push is going to get an object to start rotating. Now, the closer we are to the rotational axis, we will need to apply greater force to get it to rotate. So ideally, we want to place a force that is further away from the rotational axis. And that is the reason why you have these doorknobs that are further away from the hinge. If we apply any force that is parallel to the door, so this is what it means, it is parallel right here, then the door, nothing's going to happen. If you try to push on the door in that direction, try it, and you'll see what would happen, which would be nothing. All right. So torque is a vector, just like force is a vector. Now there's a relationship between torque and force. As you have seen in the previous thought experiment, we are actually applying forces on the door, which causes an angular force. So the relationship is that the torque is equal to R cross F. And the magnitude of the torque is just going to be RF sine of theta. The SI units is newtons times meters. The direction of the torque can be determined by the right-hand rule, which is you take your hand, you curl your hand towards the direction of rotation, and your thumb will tell you the direction of the torque. Counterclockwise is positive direction and clockwise is negative direction. Let's look at an object. Let's say we have an object of mass m that is sitting on a frictionless tabletop. It is rotating around in a circular path. It is connected to a string, and that string is nailed in the middle of this table. Now, in order to get this object to rotate, I need to apply a force which is tangent to the curve, as is shown here. So this force, tangent force, is going to result in acceleration of an object. That is just Newton's second law. F net force is equal to ma. Now if I multiply both sides by r, just doing some tricks here, I'm going to multiply both sides by r. I have F tangent times r is equal to mr a tangent. Well, a tangent is equal to r times angular acceleration. So I'm going to substitute that in. So then I get that F tangent times r is equal to mr squared times angular acceleration. All right. For this object, torque, and this stated in the previous slide, is equal to the magnitude of the torque. Let's talk about that. That is r f sine of theta. Right. R is the distance from the rotational axis where the force is applied. And theta is going to be the angle between those two vectors. As you see here, the angle between those two vectors is 90 degrees. So the torque, the magnitude of the torque, is equal to r times F tangent. So which I have substituted in here. That F tangent times r is the torque. That is for a single object. But what if we have a lot of objects? We have a mass distribution such as this. So one way we can calculate the total torque is by calculating the torque due to individual masses, point masses, and then adding them up. Okay, so which is just going to be applying this simple equation that we have derived in the previous slide now, but we're applying to single objects. So the net torque is just torque due to object 1 plus torque due to object 2 plus torque due to object 3 and so forth. Well, torque due to object 1 is just going to be m1 times r1 squared times angular acceleration. For object 2 is m2 r2 squared times angular acceleration, as though for. More compact way of writing this since angular acceleration is the same because all of these points are located on a rigid body, then we can have this summation. And as you remember, this term was what we defined as moment of inertia. So this is another way of coming to the conclusion of what moment of inertia is. Moment of inertia is the mass distribution. If you look at Newton's second law now, substituting that in, we get that net torque is equal to I times angular acceleration. Angular acceleration is a vector quantity, and we're multiplying that by I, which is a scalar quantity, and we get vector quantity at the end. Just that net torque is equal to I times angular acceleration. This equation is very similar to the Newton's second law in linear term, which we had F net is equal to m times a. Remember, see, these are linear quantities, whereas now we are dealing with angular quantities. Okay, we'll talk about torque in the next two chapters as well, so I will not go much further into that. Static is the study of forces in equilibrium. Equilibrium just means that everything is in balance. Static equilibrium means that objects are stationary. The word static translates to stationary. Now, when an object is in equilibrium, which will imply that the object does not accelerate. That is, if the object is in static equilibrium, there will be no acceleration. So there shouldn't be any linear acceleration, and there shouldn't be any angular acceleration if the object is in equilibrium. Well, there are two conditions of equilibrium. One is that vector sum of forces must equal 0, which is just saying F net is equal to 0. Well, force is a vector, so we have to apply this condition in our three dimensions. Usually you will only see it in the x and y, but it can also be applied in the z direction. So F net in the x direction is equal to 0, F net in the y direction is equal to 0, and so forth. The second condition is that objects should not rotate. There shouldn't be any angular acceleration if the object is stationary. Right? If something is stationary, that means it's not moving. So acceleration is 0, and it should not, if it's stationary, it means it's not rotating as well. So angular acceleration should also equal to 0. So the condition 2 is that the net torque is equal to 0. If the object is at rest, it is said to be in static equilibrium. These are the two conditions, which really ends up being three conditions, because most of the problems you'll see will only go into x and y, and then you have the net torque is equal to 0. So it ends up being three conditions that needs to be satisfied if the object is at rest. Let's start with this example problem. Here it says we have two children. They are balanced on a seesaw of negligible mass. The first child has a mass of 26 kilograms and sits 1.6 meters from the pivot. So you can see it in the diagram on the bottom right. There is a pivot point. There's a child 1 that has a mass of 26 kilograms. So we can calculate the weight, which would just be 26 times 9.81. R1 is the distance from the rotational axis where the child is sitting, which in the problem it tells us that that is 1.6 meters. Right. So now it says if the second child has a mass of 32 kilograms, how far is she from the pivot? So we want to figure out what is R2. That is our unknown. We know the mass of the second child, so we know the force of gravity, or her weight, which would just be 32 times 9.81. So that's A. A is asking us to figure out what is R2. B then says what is the force of the pivot, which is a supporting force exerted by the pivot. Now, with the problem with static equilibrium, you always want to start with the second condition of equilibrium, which is that net torque is equal to 0. I'm going to set my rotational axis to where the pivot is. So that is where my setup is rotating. My seesaw is rotating at this point here. So as you remember in the previous lecture, torque can be written in a couple of ways. One is that torque is equal to RF sine of theta. This is magnitude of the torque. Magnitude of the torque is equal to magnitude of R, magnitude of F, and sine of theta, where theta is the angle between R vector and F vector, because R and F are vectors. But when we use this equation, we are only looking at the magnitudes. So since I have, let's see, I have 1, 2, 3, I have 3 forces. So I'm going to say this is net torque would be torque due to object 1 plus torque due to, let's say these are vectors, torque due to object 2, and then torque due to the force at the pivot. This is equal to 0. All right, I need to figure out their directions. To figure out the direction of the torques, remember clockwise is negative, counterclockwise is positive. You can imagine, so let's say if I want to figure out what is the direction of torque 1, which is due to weight 1, I can imagine the other two forces are not there. And if that is the force that is acting on this seesaw, then the seesaw is going to rotate in this direction. Well, it doesn't rotate completely in that direction because there's a ground that stops it. But the rotation is in counterclockwise direction, right? So torque due to object 1, this is going to be positive. And I can do the same thing, but for my second object. So if that's the only force that is acting on this system, then this is going to rotate in this direction, which is a clockwise direction. Clockwise is negative, so torque 2 is actually negative. And then for the pivot force, well, that is located at the rotational axis. So the torque due to the force of the pivot is actually 0. Because as you can see, if you want to calculate torque due to the force of the pivot, well, what is R for that? It is that force is located exactly on the rotational axis. So R is 0. Now then that tells us that the torque 1 plus negative torque 2 is equal to 0. So torque 1 is equal to torque 2. Well, torque 1 is going to be R1 F1 sine of theta 1. This is equal to R2 F2 times sine of theta 2. Well, R1 is the distance from the rotational axis where this force is applied. That is 1.6. Force is just m times g, so 26 times 9.81. And then when we are to determine the angle, you have to look at the angle between R vector and then the force vector, which you can see here, they're perpendicular to each other, so they're 90. So the angle is 90, and so sine of 90 is 1. Do the same thing on the object on the right. Well, we don't know what R2 is. We know F2, which is just the mass of the object, times 9.81. And then the angle here, as you can see, this is also perpendicular, these two vectors, so sine of 90. Sine of 90 is 1. Or you can divide both sides by 1. That cancels out. 9.8 cancels out. And then you can solve for R2, which would be just 1.6 times 26 divided by 32. Should come out to about 1.3 meters. So we solved this problem, well, part A of the problem, by just looking at this, just using the second condition of equilibrium. Now, in order to answer the second part, what we will do is we will just look at the first condition of equilibrium. So the question is, what is Fp? The first condition of equilibrium tells us that net force is equal to 0. And if you look at these three forces, they are in the y direction only. So we only need to apply that condition in the y direction. So this would just be F net in the y direction is equal to 0. You have Fp minus 20, it should be plus negative, which end is just negative, which is just minus, right? So minus 9.81 plus 32 times 9.81. The negative is because of their direction. And then you can solve for FP. In this problem, we were told that there is a floodlight which has a mass of 15 kilogram. So there's a gravitational force on the floodlight that is attached to a rope which is connected to a beam. The mass of the beam is negligible, which tells us we don't have to take into account the gravitational force on the beam. And then there's a rope that is supporting the floodlight that is going at an angle of 30 degrees. In addition to that, there has to be some support forces from the pole on the beam. The question is asking us to figure out what is the tension in the cable, and then it asks us to figure out the horizontal and the vertical forces that are exerted by the pole on the beam. There's a typo here. These two words should be flipped. All right. So to do this problem, you can start by just making a diagram of forces that are acting on the beam. Now, we are not interested in the forces that are on the floodlight. So if you look at the floodlight, since it has mass, there will be a gravitational force. Let me call this mg. We're given the mass, so we can calculate that gravitational force. But it is connected to a rope, so there is going to be tension in the opposite direction. Right. Tension is transmitted throughout the rope. So this rope that is hanging is different than the rope that is at a diagonal. So if that is the tension force, then there's also going to be tension here. And that tension is the same as the tension there. Remember, we talked about how the tension force acts away from the mass in the direction of the rope. So if you're looking at the beam, if you're interested in the forces that are acting on the beam, then our tension is going to be in this direction. This tension is the same as the tension here, and that tension is equal to mg. So this is equal to mg. Let me call this something else. Let me call this F1, because we have another rope and we need to calculate what is the tension force in this rope. All right, so this is tension. That's F1. And then by the pole, we have a couple of forces. You can label them as F2 and F3. Now I'm going to redraw this diagram, but I only want to look at the beam itself, because the other things can be a little confusing, and I'm going to label all of my forces. We always start with the second condition of equilibrium, and to do that, you need to figure out where do you want to place your rotational axis. So I will place it here because this is the most convenient place for me to pick, and that is because if I place it there, F2 and F3 cancels out because they're located at the rotational axis. So then the sum of the torque will be the torque due to F1 and torque due to T. Well, these are actually vectors. Okay, so torque 1, we have to figure out the direction of the torque 1. So if that is the only force that is acting on this beam, then the beam is going to rotate in the clockwise direction. So that would be negative. And we're going to only consider the magnitude of that torque then. And then due to tension, it is going to be rotating in counterclockwise direction, and counterclockwise is positive. Now torque due to the magnitude of the torque is just going to be F1 times R1 times sine of theta 1. F1 R1 sine of theta 1. Well, if I look at F1, that is just going to be mg. M is the mass of the floodlight. R is going to be from the rotational axis, which is at the end, to the end of the beam, which I'll call it L instead of R. It doesn't really matter what you call it. We don't know that value, but you'll see that it will cancel out. And then we want to figure out what is the angle between these two vectors. As you can see, F1 is perpendicular to R, so the angle is 90 degrees and sine of 90 is 1. So the magnitude of torque 1 is mgL. Now we can calculate the magnitude of torque due to tension, which is going to be tension, which we don't know what that is. Where is that tension applied? It's at the edge. So I'll call that L as well. And then sine of the angle between those two vectors, which is here. And as you can see, T is not perpendicular to the beam, so there is an angle of 30 degrees. And I'm going to substitute everything into this equation here. This, I don't know where this 3 coming from. Just cross that out. And then you'll see plugging in the numbers, canceling out L's. I can solve for T, which comes out to 294 newtons. Okay. To answer part B, we are looking to find out what is F2 and F3. So we're going to use the first condition of equilibrium, which is F net in the x direction is equal to 0, F net in the y direction is equal to 0. So we'll start with the x. In the x direction, I have F2 that is pointing to the right, which is positive. But then I have this component of the tension that is pointing to the left. And if I know this angle is 30 degrees, then this side that is touching the angle is just going to be T times cosine of 30. It is pointing to the left, and that is where this negative sign is coming from. We know what tension is from the previous slide, so we can plug it in and we can calculate. So when we do this calculation, F2 is about 255 newtons. Do the same thing in the y direction, and you'll see that in the y direction there is no force. F3 is 0. So that means this is not out there. And that should make sense to you. If this beam is just horizontal like this, then there's a normal force that is exerted by the pole on the beam, and that should be in this direction. All right. This example problem very similar to the previous one, but of course there's no ropes. It looks like there's a lot going on, but if you follow the steps, you should see that this is no much difficult. So let's read out the problem first. The problem states we have a uniform ladder which has a length of 5 meters and it weighs about 400 newtons. Remember how in the previous the beam didn't have a mass, but this ladder does have a mass, so there will be a gravitational force on this ladder. It's a uniform ladder, so that means the gravitational force is going to be at the center, at its center of mass. So this is the 400 newton. The ladder rests against a slippery vertical wall. So since it says it's slippery, that means there's no friction on the wall. The incline angle between the ladder and the rough floor, well, there's a rough floor, so there is friction, is 53 degrees, which is labeled here, from the wall on the ladder, and the coefficient of static friction at the interface of the ladder with the floor that prevents the ladder from the spring from slipping. So what we need to calculate, it says find the reaction force from the floor and from the wall, and mu sub s. Okay, so you start out with drawing out the diagram. So if this is touching the floor, then there is a normal force. Let's call this N1. And if this is touching the floor, then there is going to be a normal force by the wall, which is N2. Why are they in this direction? Well, you have to look at the surface that is in contact. In addition to that, there's no friction on the wall, but there's friction on the floor. Okay, so this ladder is trying to move in this direction. Okay, so it's going to slip that way. So the friction is going to oppose that. So the frictional force is going to be in this direction, which is supposed to be just horizontal direction. This is force of static friction. This object is in static equilibrium. These are the forces that are acting on this object. So if I want to calculate N2, let's start with calculating N2 actually. So what I will do is I will place my rotational axis here. Say that the object is rotating at this point. It doesn't matter where you place it. It doesn't mean that is incorrect. It's just it is more convenient to place it here because then it cancels out N1 and torque due to N1 and the torque due to force of static friction. I will start with the condition of equilibrium. The second condition, which is net torque, is equal to 0. So I have torque due to N2 plus torque due to the 400 weight. That is equal to 0. These are vectors. I need to figure out their direction. If 400 Newton is the force that is acting on this ladder, the ladder is going to rotate in this direction, which is a clockwise direction, so that is negative. Get rid of this. And then if N2 is the only force acting, then it's going to rotate in this direction, which is a counterclockwise direction, so that will leave it as positive. Torque due to N2 is going to be N2 times R. R is the distance from the rotational axis where the force is applied. So it would be this, which is just the length of the ladder. That's 5. And then sine of the angle between the ladder and N2, which would be this angle here. Okay, so well, I don't know what that angle is. Well, I know from geometry you can figure it out, which is also going to be 53 degrees. So this is sine of 53 minus force, which is 400 newtons, times where that force is applied. That is applied at 5/2 in halfway point, and the angle between these vectors here. Well, if you look at it, this is just a triangle. This angle is 53, and this is a right triangle, so this angle here is going to be 90 minus 53. Okay. So what is that angle? Okay, correct. That's correct. So it's just sine of 37. That is equal to 0, and we can solve for N2. This is 5, so N2 times 5 times sine of 53 is equal to 400 times 5/2 times sine of 37. The 5 cancels out, and N2 is just 200 times sine of 37 over sine of 53. This actually comes out to about 150 newtons. Say 151. Okay, so now if I want to calculate what is N1, that is going to be pretty simple. So I can apply the second condition of equilibrium. Sorry, it's actually the first condition of equilibrium, which is F net is equal to 0. So I'm going to apply it in the y direction because N1 is in the y direction. This is equal to 0. So now if I look at what are my forces in the y direction, I have N1 and I have this weight. So this is going to be N1 pointing upward plus negative 400 is equal to 0. So then N1 is equal to 400. Now let's look at force of static friction. Well, force of static friction has to equal to N2. So force of static friction by Newton's second law is equal to N2, which is 151 newtons. Well, force of static friction, the maximum value of force of static friction is mu sub s times the normal force. Well, normal in this case is N1. This is equal to 151. So plugging that in, so I have 151 divided by 400. That comes out to about 0.377. So as you can see here, these values are incorrect. This value is fickly. the work here is correct.